Okay, here we go. Section 2.7, absolute value functions and their graphs. Objective to graph absolute value functions. So I've given you some examples. The absolute value function is obviously absolute value of x. A couple things you need to know about it. First of all, the axis of symmetry. The graph is symmetric about this vertical line. So there's going to be a vertical line that if you fold it in half would be the same on either side. We'll be able to identify that. This next part about the vertex is not in the book, but I'm going to give it to you anyway, because I know if you take college algebra, it is in that book and then you'll have already seen it. So the vertex is either the maximum point of the graph or the minimum point. Remember that the absolute value graph is like a V. So it'll be either look like a V or it'll be flipped upside down and kind of look like just one peak of a mountain. So the vertex is either the maximum or the minimum. This formula, negative b over 2a, and f of negative b over 2a is something that we'll use in other lessons as well. So this particular lesson, it might not be set up that way, but I'll show you kind of how that works in a minute. The b and the a actually come from this equation right here. Ax plus by equals c, that's kind of like standard form. So the a is with the x, the b is with the y, and then the number. So negative b would be whatever your y is, that number that goes with it, over 2 times a. It's kind of like if you take this equation and plug it into the quadratic formula, that's exactly what you're doing. So that's how those letters kind of come about. The f of negative b over 2a is whatever you get for this first part that's your x, you plug it back in to see what your y is, okay? And like I said, it might not show like this today, but we'll be using it throughout the course. So here's some key concepts. They have a table with a bunch of ordered pairs. They went from -3 to 3. They actually define the function. Absolute value of x equals x when x is greater than or equal to 0. So basically remember, when you have absolute value of a number, it always is a positive number coming out. And like if you had absolute value of a 7, it's 7. So when your number is bigger than or equal to 0, you just get that positive number out. When your number is less than 0, in order to change the sign, that's why they have that negative sitting outside of it. So it looks really funny here. It looks like it should be opposite, that your answer should be negative, but it isn't. It is what is negative -7, and that would be positive. So either way, you do get a positive number. The vertex here is at 0, 0. The axis of symmetry would be x equals 0, that vertical line that's going through it, that if you fold it, it would look the same on both sides. Okay, so here's the first one. What is the graph of the absolute value function? Y equals absolute value of x minus 4. How is this graph different from the graph of the parent function, f of x equal x, or absolute value of x? So what is this? First of all, thinking about what we learned yesterday and on Thursday, what does this do? Down 4. So we would expect that our original absolute value function, which looks like a V, starting at 0, 0, is going to go down 4. Okay, so those rules still apply. And let's graph it. They don't tell us we have to do a table, so let's not.
So those points that they have in the book, in the Y column,
yep.
Are those random?
Are they giving us the x values?
Yeah, it's
-3 to 3. So they're plugging them in and getting what you actually get. Okay, so, yep. Okay. I'm going to do the parent function first, and then I'm going to graph the other one after that, because we know already what this is going to do. So my parent function I'm going to put in pink. And then the other one we'll do green. Okay, so they use -3 all the way to 3. As long as you do a couple on either side of where that vertex is, you're fine. If you don't want to do a table, if it doesn't ask for it, that's also fine, because most of these are pretty easy to plug your numbers in. So if I plug in a 0 into that first function, I get 0. If I plug in a 1, I get 1. If I plug in a 2, I get 2, and so on. So it keeps going that way. Remember that these are basically folded in half over that axis of symmetry, and that could look like... Now, I did more points because they're super easy once you know where they are. So if I plug in a -1, absolute value of -1 is 1. If I plug in a -2, absolute value of -2 is 2, and so on. And I don't necessarily have to put it into a table unless it asks for it. So now I'm just going to draw it in. And yep, I plugged it in the pink one. Absolute value of 1 is 1. Absolute value of 2 is 2, and it forms that V. And then I plugged in the negative side as well. So we already said that that -4 brings it down 4. So couldn't we just move all those points down 4 and do it that way? And we can also put it in a XY table as well. So let's move it down, and I'll show you how it works both ways. I'm just moving every single point that I graphed originally down 4. Okay, that point kind of moved. So again, if we plug in points, it will be absolute value of 0 is 0, 0 minus 4 would be -4. So it'd be the order pair 0, -4. If I put in a 1, I get 1 minus 4, that's -3. If I plug in a 2, I get -2, and so on. And we could do the same on the other side. Now, the axis of symmetry this time, and I'll identify that too because you might have to do that, is X. Wow, everything's moving here. X equals 0. Now I put a dotted line on that vertical. They don't always have to be on the x-axis or y-axis. They could move them anywhere, but they're going to probably stick to some standard ones in this book. The transformations you studied in 2.6 also apply to absolute value functions. Here are your parent functions. It's just kind of like the summary all on one page. If you know them from the other page, it isn't something that you necessarily have to write down, but you certainly could. You won't be able to use it on the test, but here it is. So for a vertical translation, you are looking for this plus K or minus K. If it's a plus K, it's moving up that many units. If it's a minus K, you're moving down that many units. The horizontal translation, remember that if you have a minus inside the function, and that means within that absolute value function, a minus will move it to the right that many units. A plus will move it to the left that many units. And I'm going to tell you why that actually happens here in a little bit when we look at standard form of a absolute value function. The vertical stretch is when the number sitting right in front of it that's multiplied is bigger than 1. A vertical compression is when you have that fractional number out there. And by fractional number, I mean between 0 and 1, because the other ones could be a fraction too. But if it's bigger than 1, it's a stretch. If it's less than 1 but bigger than 0, it's a compression. And then the reflection part. If the negative is outside the function, it reflects over the x. If it is inside the function, it reflects over the y. So rules are exactly the same. They just look different because they're absolute value this time. Okay, so what are the transformations that go with this equation? Y equals absolute value x plus 2 plus 3. So what does the plus 3 do? That's always the easiest one. Up 3. Okay? You can do them in any order. It doesn't matter at all. Now, is this other plus 2 inside the function or outside it? It's inside because it's in those absolute values. So now we have to think about what did we write on the other page. If it's inside the function, that means it's the right left. So a positive 2 really means what direction? Left 2. And as long as you have the left 2 somewhere and the up 3 somewhere, that's the transformations that you're using. So it's kind of like you're putting this equation into words by explaining what's happening. On these, you don't have to graph them. It just says what are the transformations that go with this equation. We happen to do the up 3 first, and it wouldn't matter if you had the order switched. So as long as you have the two things, that's what we're looking for here. There isn't an A that's sitting out in the front, so we don't have to do that. And there isn't anything that flips it over the X or Y axis, so we don't have to do that either. Think about every single one of them, though, to see if there's a number that goes with each one. How about the next one, the got it question number 2? Let's do the inside of the absolute value first. Right 2, because it's a minus this time. That would mean right 2. And then how about the plus 1? Up 1. So as long as you have those two things somewhere, that's what we're looking for. Here they talk about vertical stretch and compression, and these are really the same as what we did yesterday. What is the graph of 1/2 absolute value of x? So the 1/2 is between 0 and 1, right? So it is a vertical compression. Think about that before you do it so you know this one looks like the regular V graph, only it's smushed down and it kind of looks a little bit shorter and a little bit fatter. I'm going to do just a little XY table on this one just so you can kind of see them before you put them on the graph. Sometimes when you're working with fractions, it is nicer to actually see what number you're looking at. If I put in a 0, don't I still get 0? Yeah, so I'm going to go -2, -1, 0, 1, 2. So 0 is still going to be 0. If I put in a -2, absolute value of -2 is 2. And what's 2 times 1/2? 1. If I put in a -1, absolute value of -1 is 1. And then 1 times half is half, or 0.5 if you want to put that. Wouldn't the other ones be the same? So again, with absolute value, you always have a positive number out. So I am just going to repeat my numbers. My 1 would be the same as my -1. My 2 would be the same as my -2. And then I can put them on the graph. So -2, 1, -1, 1/2, and then they would be the same on the other side. So notice how instead of a more upright V that we had before, it's kind of shorter and chunkier. Here's the original one. It's skipping again, sorry about that. Here we go. Sorry when you guys are watching these. Okay, so it was 1, 1, 2, 2. The original one here is in green. So notice how when it's a compression, it just takes both sides and just smooshes them down a little bit. And it would be half the size, which also makes sense. So if you can take these ordered pairs and say, okay, the original one is sitting at 1, it needs to be half as big, you could do it that way too. Yep.
So is the parent one always y equals x?
Y equals absolute value of x? Yes, for this one. Yep. Yep. So now notice if we go to 2, 2, the y part, what's half as big as 2? 1. So you don't have to use an xy table, even though that is basically what we're doing. If you know that the y part's supposed to be half as big because it's a vertical compression, do that. Take your y value and take half of it, and you would get the points very easily that way too. But you'd have to graph the parent function first. Yep. The green one. Yep. So green is y equals absolute value of x. Yes.
What numbers are you plugging in for the green one?
For the green one, I'm using y equals absolute value of x, so that's the parent function, which is the one that this one goes with, the original one. So you could either plug points in for that, or you could take the y values for that. So it starts at 0, so absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2, and then this function is half as big for the y values, so you would take and just divide those y values by 2. So they would be half as big. Bring it down and make it half as big. Okay, so here is where I'm going to explain kind of how they get the right-left thing. General form for an absolute value function is right here. Y equals a, and of course that determines if it's a stretch or compression. X minus h is in the absolute value, and then plus k at the end. Your vertex is located at hk. Notice how if you look at that x minus h that's in the absolute value, it's kind of like if you set that equal to 0 and solved it, you would get x equals h. That's why it is the opposite of what it kind of looks like. So when there's a subtraction in there, you're just grabbing that h out of there because the subtraction is in the standard form of it. So the compression or stretch factor is the absolute value of that a, and then the axis of symmetry is x equals h. So kind of remember what those things are. This time, they're not doing a lot with that negative b over 2a and f of negative b over 2a, so I just want you to see it. We're not going to actually have to use it a lot because they don't give us quadratic formulas. Eventually, when we get to parabolas, the standard form of a parabola is going to look very similar to this one. Instead of the absolute value, you're going to have parentheses around it with it squared. So this will look familiar later as well. Okay, so without graphing, which is a bonus, right? We all love graphing. What are the vertex and axis of symmetry of the graph? How is the parent function transformed? So we're going to have to describe it. What are each of those numbers doing? We're also going to have to just say what's the vertex and the axis of symmetry. So the vertex we'll do first. I'm just going to do v equals. What we need to do is just pull out two specific numbers. The two numbers are 2 and 4. Okay, so remember that your standard form looks like this.
Do we take in the negative 2?
Nope. Okay, so that's the standard form. So just the 2, just the 4. If that were to be -4, then of course you'd grab the -4 for that one. But basically, you're looking at the opposite of whatever the sign in the middle is for that H part. Yep.
So why don't we grab the negative?
Because when it's kind of like this, x minus 2 equals 0, x would be 2. Since it's a quantity, you have to get it by itself, which would change the sign.
If it was a plus, it doesn't.
Then it would be a negative.
Okay.
Yep.
So it's the opposite.
Opposite of whatever the sign is, just for that one. Okay? So axis of symmetry is just what I did right here. If you grab that part that's in the absolute value and you solve it, it would be just x equals 2. Now we have to describe the transformation. Okay, so what about the 3 on the outside? Is it a stretch or compression? Vertical stretch
Wait, how do we number it again?
of 3. The A part on this one, this is the A. Whatever number that is, take the absolute value of it. If it's between 0 and 1, it's a compression. If it's bigger than 1, then it's a stretch. So vertical stretch of 3. What about the -2? Would that be a right 2 or a left 2? So right 2, remember it's the opposite, so we'll go right 2. And what about the +4 on the end? Up 4. Now, obviously on these, for graphing them, it would be a little bit harder. You would originally graph your V at 0, 0, 1, 1, 2, 2, -1, -1, -2, -2, and then you would have to do all of these things. So you'd have to move it right 2, you'd move it up 4, and then you'd have to stretch it by 3. Lot going on in this one, okay? They didn't have us graph it, but that's what you'd have to do. So many times they'll graph the original one and they'll do one step at a time. So they'll maybe move it right 2 and up 4. And then once you get there, then you would do the stretch or compression from there. It doesn't matter what order you do them in, as long as you do all 3 of them eventually. Okay, same thing on this one. What are the vertex and axis of symmetry of this one? So you guys tell me what the vertex is, just by looking at it. Okay. Everybody agree? 1, 3? Sure? Close. There you go. 1, -3. So this one is just the number for the 1, and you have to grab this sign for the -3. So 1, -3. Axis of symmetry this time. Yep. And you have to make sure you grab x equals 1. So I'm going to say x equals 1 because it has to be an equation. And now we will describe it. So what about the -2 part? Vertical stretch or vertical compression?
So if it's a negative, it'll be a compression?
No. It's always absolute value of whatever number that is, so it's really looking like a 2.
Okay.
Since 2 is bigger than 1, it's a stretch again. So vertical stretch of 2. If it was like -1/2 or something, or half, then it would be a compression because it's between 0 and 1. Then what about the -1 in the absolute value? Is that right or left? Right 1. And what about the -3 at the end? Down 3. So much easier to just describe in words than to actually graph it. So this one, I would probably take my original absolute value function and I would move it right 1 and down 3. And once I got it there, then I would do the stretch of 2. So I would take the y values and multiply them all by 2. The x values would stay the same. And of course, you could do ordered pairs for that if it was hard for you to just kind of look at them and do it. But again, it doesn't say to graph it anyway. Now, sometimes they're going to make us take the graph and write the equation from there. So the first thing you'll want to do is identify the vertex, which is that point at the top or at the bottom. So this point is the vertex. and we just have to identify what it is. So it is -1, 4. Okay, now how does that help us? When we're actually trying to write it, we are trying to plug it into this equation. So my h is a -1. Okay, so I'm going to start writing it in there right now. So generally it's a minus in there, right? So I'm going to go x minus a -1, which would be x plus 1 this time. My k is 4, so I'm going to put a plus 4 at the end. And now I have to figure out what happened with my a part. The thing about this is if you can find slope, that's what number goes in there. Okay, so this will be easy once you know kind of what to look for. So if I'm looking at going from here to the next point that I know, it would be a down 1, right 3, correct? So go from your vertex, find out what that next point is that you know. And the reason I didn't pick this is because it's only part way up, that's only part way up, but I know for sure that that's going through an ordered pair that I could identify. So I got it outlined. I don't know how I did that. Anyways, your slope basically, so I'm going to say, wow, it's like magic. Okay, my slope is -1/3, and that goes there. Okay, so whatever your slope is, and it doesn't have to be going from the y-axis. So that's why I kind of put that triangle in there and counted. And this would be my function.
So for like a test, will we have all these equations?
You'll know by then. Maybe. I'm not sure yet. Okay, so let's do one more of those, and then I think we are done. So first we have to identify the vertex. So what would the vertex be? And that would be right here. Yep, 2, -1. Okay, so I'm going to start plugging these numbers in. So where do they go? Where does the 2 go? Okay, and is it minus or plus? -2. And then the sign and everything goes outside it, so -1. And then we have to figure out what is the number that goes ahead of it. So from my vertex, I'm going to go to the right. The next point that I know for sure what it is this one. So I'm going to draw in my triangle. That would be a positive slope of 1/4. So I'm going to put a 1/4 ahead of it. Okay, so these are actually, I think, a lot easier than graphing them because of that number that's sitting out in the front. So this one is a vertical compression because of the 1/4. Okay, so anybody have any questions on anything? We can go back. Yep, absolutely. This one?
Yeah, I just need to get power five. Do we need to say if it's a vertical compression or?
Nope, you just have to write the equation. So if you can write it, plugging in those numbers, you're good. So you have to plug in an A, an H, and a K. Jenna?
So, since, would that, okay, power five, would that be a vertical compression or a straight?
This would be another vertical compression on this one because of this 1/3 right here. Because it's 1/3 as big.
But since it's negative?
If you look at the rules that we had above, I'm just going to flip back one more time up here. Right here. Notice how they have the stretch or compression and the absolute value on this one. So really that negative doesn't matter. It's only looking at the number itself. Okay, so just the number. If it's fractional between 0 and 1, regardless of the sign, it is a compression. If it's bigger than 1, then it's a stretch. Okay, so remember that stretch or compression is in the absolute value, so the sign ahead of it just means it's opening down rather than up. Okay, and Avalon, did you get that? I kind of flipped from that page. Okay, this one or the last one?
This one.
Okay, okay, so I'll leave it on this one.
What's happening to the graph?
This one? This one right here?
Yeah.
Okay, so the negative means it's opening down, so instead of a V going up, it's going down.
Okay.
The 1/3 means it's a vertical compression, so it's smushing down, it's 1/3 as big.
Okay.
And then the vertex is -1/4.
Yeah, but why is it like, why does it look like this side's longer than that side?
Because the book was curved when I took a picture.
Oh.
Yeah.
Okay.
I just snapped this picture and just
There's
inserted
a
it.
lot going on in these.
There's a lot going on. So yeah, it looks
Way
weird
better
on this
than
one
yesterday.
because this was in the fold of my book and I just snapped a picture of it.
When you're graphing it, is it just like slope, like -1/3
Yes.
is literally your
Yep.
slope?
So if you can find the vertex and you can find that next point that you're using, I'm going down 1, right 3. That's what that A
And
is.
that first point, so, like,
Yep.
you get that from your vertex.
Yes.
And your vertex you get because you identify it like the 1 and the 4.
Yes.
And then the X is opposite of what it shows.
Yes.
Okay.
Yes. So the opposite of a -1 would be +1, and that's why we have a +1 in there.
Okay, so it's
Yep.
just kind of memorizing like what goes.
Yes, what goes where.
Okay.
Yep.
This is fine. So
Yes.
I created a Quizlet and
Yep.
it deleted all my definitions. Like it has like all the words,
Yeah.
but it deleted every definition.
If you close it and open it again, just to make sure there wasn't like a glitch or something.
Can I study on my phone for next hour?
Thank you.